On this page, we're going to start to take information about graphs and write the equations of those functions. So it says, write the equation of a cubic polynomial with a single root at -5 and a double root at 2. Assume the lead coefficient is -1. There are actually an infinite number of polynomial equations that go through the same roots, but if we know the lead coefficient, there's only one possible equation. So I'm going to actually draw the rough sketch first. So if the lead coefficient is -1, it means that we are decreasing like this, right, with the negative x cubed graph. So we have a single root at -5 and a double root at 2. So this graph would come down, single root, I did not draw that super straight, pretend it's straight, and then a double root at 2. Now what that means is when I write my equation, first off, I'm going to put a -1 in the front of it. If this goes through -5, the factor has the opposite value of the root, so that's x plus 5. This is a double root at 2, so I need x minus 2. And if I have a double root, it really means I have two factors of x minus 2. There's two roots that are equal at that spot. We don't usually write that. Usually we would just write the x minus 2 squared for the double root. Now there's no need to multiply out these equations. You can just leave them in this factored form. If it said standard form, we're going to do one of them. We would have to multiply everything out to have, everything multiplied out versus factored. So the next one, it says write the equation of a quartic polynomial with roots of 6 and 0 and a double root at 3. Assume the lead coefficient is 1. So I'm going to draw my little graph. 6, 0, and a double root at 3. It's a lead coefficient of 1, so that both of those arrows are going to point up. So we go directly through 0, double root at 3, and then back up through 6. So not pretty, but that's basically our shape. So when I write this equation, I don't have to put the 1 in front because it won't make a difference, but I'm going to write it there. That's where we put the lead coefficient. My first one's 0, so that just gives me an x minus 0, which afterwards I'm just going to write as x. You can notice that it would just be x. The double root at 3, so we have x minus 3 squared. And the single root at 6, so that's x minus 6. So this one specifically, I'm going to get rid of the 1. I don't really need it. This is just going to become an x. X minus 0 is x. So we don't have to simplify it, but we don't really want to leave that x minus 0. So that's the equation for the next one. Now the next one's a challenge problem. It says write an equation of a cubic polynomial with a root of -3 and 2i and -2i. So for this one, we're not exactly sure what those imaginary roots look like, so I'm just going to draw a rough sketch. This one's going to be increasing, so maybe the graph would look kind of like that. Okay, so 2 imaginary roots, 1 real root. So the easy part, right, is just lead coefficient of 1, that this is going to be an x plus 3 for the root of -3. For the 2i and the -2i, I can write x minus 2i, x plus 2i, the same way we would change the signs. Now, I don't really like to leave i's in this, this type of equation. I couldn't type that in my calculator to check it. So I would distribute these two out. These are complex conjugates. I'm just going to rewrite the beginning. I can drop the 1. So this becomes x squared plus 2xi minus 2xi, and then I have minus 4i squared. Moving further from that, the middle parts cancel just like we expect, and this is a -1. Okay, so this is going to end up being x squared plus 4 for that factor. So I don't have a ton of room, but I'm going to write it right here, just kind of squeeze it in. So this is y equals x plus 3 and x squared plus 4. So that's not something we would really test you on, but the idea is even if there's imaginary roots, we can find equations that don't have imaginary numbers in them for those. So the next thing says, no, any of these functions can be written in standard form by simply simplifying the factored form of the polynomial. So I'm going to look back at 5a. So that's this equation here, and we are going to write it in standard form. So I'm going to bring that down. Also something that I'm not really going to test you on, it's possible it could show up in a region, so we haven't seen it yet. So I'm just going to start out and rewrite the equation. I'm going to write it out with x minus 2 times x minus 2 because I'll need that to expand it. Now there's different ways I can do this. I'm going to simplify this part. I'm going to do part of it in my head. X squared minus 2x is minus 4x plus 4. And then I'm also going to multiply this negative 1 in just to kind of cut down on the step. So that's negative x minus 5. And that's just using the associative property. We can do whichever part we want to first when it's all multiplication in a row. So from here, I would further distribute. So this is going to be negative x cubed, and then plus 4x squared minus 4x. And then the second set of distributions, minus 5x squared plus 20x minus 20. So I'm going to write my answer simplified right here. So that's going to be my only term with x cubed is the first one, so I have negative x cubed. That's minus 1x squared or minus x squared plus 16x minus 20. So something else which is on the next one that we did used to teach was how to find the actual equation when you don't know what the lead coefficient was. On all the ones above, we said it's either 1 or negative 1 and just kind of kept it simple. What we would need to know the actual number that's in front without telling it is one more point on the graph. So for example, it says, in the function in exercise 5, if the function in exercise 5a passed through the point 3, negative 24, find the lead coefficient. So basically, this is telling me how stretched out the graph is from the y-axis. So I'm going to start from the 5a answer, not the one I just simplified in exercise 6. So I'm starting from this equation. Let me just get something to underline it, and I'm going to write that at the bottom. So I have y equals negative 1 times x plus 5 times x minus 2 squared. Except now, I don't know the lead coefficient is negative 1. I'm going to put an a here because we're trying to find out what that lead coefficient is, and we're going to use this point for that information. So basically, all we have to do when we don't know the lead coefficient is plug in the point 3, negative 24 for x and y. So the y is negative 24. We don't know the value of the lead coefficient. Here, this would be 3 plus 5, and then 3 minus 2 squared. So we have negative 24 equals, this is 8 times 1 squared, so that's going to be an 8a. Divide by 8. And if that's a point on the graph, the lead coefficient would be negative 3. So here, my equation would be negative 3 times x plus 5 times x minus 2 squared. So exercise 7 and exercise 6 are both kind of extensions. The first one is, in exercise 6, we learned that we can stretch these out into standard form, and that's, kind of what we saw in the other units was not being factored. It is actually equations like that, and in the other lessons. On exercise 7, we saw that to find the exact equation without telling us the lead coefficient, we would need one other point other than the roots on the graph. So moving to the next page, we're just going to look at a couple of extension questions. This is back to your standard questions. Here we have a picture, and we want to write the equation, and we are once again assuming that the lead coefficient is either 1 or negative 1. Now here, I do have to decide, is the lead coefficient 1 or negative 1? I can tell this is an x to the 4th graph, and because both arrows are going down, I can tell it's negative x to the 4th. So that tells me here the lead coefficient is negative 1, okay? I have a single root at negative 3, so that gives me a factor of x plus 3. I have a double root at negative 2, so that gives me x plus 2 squared. and I have a single root at 0. So I'm going to squeeze in here the x that would go with that single root at 0, and that's my equation. Whenever there's that root of 0, it gives us a factor of x minus 0, which becomes x, and we always kind of put that towards the front. The second one is a cubic, so it's x cubed, and I can tell it's positive x cubed because of the direction. So for this equation, I can put a 1 in the front, I don't need it. Root of negative 5 gives me x plus 5. Root of 0 gives me an x, which I'm going to squeeze in the front. Root of 3 gives me a factor of x minus 3. We don't have to put these in standard form. I can tell if I did multiply it out, I would get an x cubed graph, which is what I'm looking for. The last two problems at the bottom are a little more general because they don't tell me the value of the zeros in terms of having an exact value. They just put variables there. So we're going to write general equations without numbers to plug in. So looking at this first one, first off, this is negative x cubed. So when I write my equation, I'm going to put negative 1 for the lead coefficient. There's a factor of negative, or a root of negative b, so I have a factor of x plus b. Double root at c, so that's x minus c squared. Looking at the second one, this is a positive x cubed graph, and if you have trouble with that, that's back to that first lesson about power functions and the directions and end behavior of those graphs. So here I have a positive 1. It's a double root at negative c, so I have x plus c squared, a single root at b, so that would be x minus b for that graph.